Let's start, Sean. Okay, so it's a pleasure to welcome Sean Welleck today for a talk on from decoding to meta generation and inference time algorithms for large language models. Sean is an assistant professor at Carnegie Mellon University in the School of Computer Science and in the Language Technology Institute. He graduated from New York University and did his postdoc at University of Washington. So he's author of popular methods in natural language processing and machine learning, unlikelihood training, and many others. And he did pioneering work in mathematical reasoning using large language models. He's also the author of a podcast on thesis reviews, which many of us know. And today he's going to give this talk that is a survey on meta generation. And it's also a special edition of a tutorial that will be also featured at NeurIPS this year. Thank you, Sean. The floor is yours.
Okay, thank you, Zaid. And thanks so much for having me here. I'm really excited to give a talk today. Today I'm going to talk to you about inference time algorithms for large language models. And at its core, today's talk is really about algorithms for generating outputs with a language model.
Sean, could you speak a little bit louder? Yeah.
Sure.
Okay.
Okay. Is this good?
Yeah, this is good now.
Okay. And so why should you be as excited and as interested as I am in this topic? Well, one thing that a lot of people in the field right now are thinking about is how we can use compute at test time to improve the performance of a language model. And so the algorithms that I'll tell you about today give you some ways of doing so, and importantly, give you a kind of conceptual framework for thinking about what has been done and where things are going in the future. And also, the talk is about language models, which themselves are pretty exciting, because it seems like every day people are doing new things with them, ranging from solving Olympiad problems to writing code in their code base, and essentially anything that could be framed as generating some sequence. And if we think about progress in language modeling, we can think of it from the perspective of scale. So the first wave of scale had to do with scaling the amount of compute that was used at pre-training time. So this is a really famous result from OpenAI, and they showed that here on the x-axis, as you increase the amount of compute that's used to pre-train a model, which is based on the size of the model and the number of tokens that the model is trained on, the performance of the model predictably improves here in terms of the test loss. And so this is really exciting. But what people found is this, at least so far, hasn't really led to the models being able to do all of the tasks that they wanted to do. So this actually led to a second wave focused on what is called post-training, where we take an existing model and try to train it further. So here's a really famous paper from Google, and they essentially collected a lot of input-output pairs for different tasks. You could then fine-tune the language model on them, and it does better on the tasks and even can generalize to some new ones. And so this has led to, these very useful assistants that can do things like follow instructions you give them. But so far, this hasn't really been sufficient for doing everything that we want to do with a language model, things like solving really difficult problems or writing really complex code. So recently, there's been a kind of third shift happening, and it's really around scaling the amount of compute that is used with a trained model at test time. And so throughout the talk, I'll use the terms inference time, test time, and generation time interchangeably. And so here's a kind of famous plot from a recent model from OpenAI called O1. And you can see on the x-axis that they have the amount of test time compute that's being used by the model, and the accuracy on this pretty difficult mathematical reasoning benchmark increasing. Okay, so recently Sasha Rush gave a talk trying to figure out what is being done in O1. I actually also don't know, but we can look at what has been done in the field and try to get an understanding for how we can use test time compute to improve the performance of a model. So since we're using language models, one way to increase the amount of compute we're using is to simply just generate more tokens. When you think about it, each time you're doing a feed forward pass to generate a token, it is in some sense using more computation. And so this is a really influential method called chain of thought. And they found that essentially by prompting the model to generate this intermediate thought sequence shown in green, it could actually have a large impact on the way that models were scaling for different reasoning tasks. So for example, here, looking at the right-hand side for these poem models, we can see that with the black line, it didn't really look too promising to simply scale up the size of the model if you were just asking the model to kind of give you an answer. However, if you just ask it to generate these intermediate thought tokens, then the scaling behavior completely changes. Now, there's a variety of reasons for this, but for the purposes of this talk, we can view this as being one way of just kind of spending more compute by generating these tokens. Second, we can just call a language model multiple times. So here's a famous example called AlphaCode. And you can see on the left-hand side that their system has undergone these two stages that I told you about. So pre-training and then fine-tuning on these problems and solutions. Then when they use their system to generate new programs, these are like competition-style programs, they don't just have it generate one output program, but instead they have it generate thousands or even millions of programs. Then they filter them and cluster them and ultimately choose just a small set that they run and consider to be the output of the system. And this also can have a dramatic impact on performance. So you can see here on the x-axis, as the number of samples that you're using increases, the pass rate on the y-axis is increasing a lot for a wide range of different sized models. And then third, another shift that's happening in the field is thinking about how we can take a language model and also incorporate other components into the generation system. So for example, you could have a language model, but also a separate model that learns to evaluate or verify sequences. You could try to call out to a calculator, or if you're writing some code, call out to a code interpreter. And so these are different ways of kind of offloading computation away from your language model, and they can also be very beneficial in practice. So how do we think about these things in a kind of common framework and look at the patterns that have been developed for achieving them? So today I'm going to tell you about a framework which is called meta-generation algorithms. Let me first tell you what a generation algorithm is, though. So a generation algorithm just refers to any algorithm that you use to produce an output sequence with a trained language model. So you can think of this as like calling a language model API, or you might have an inference library that you're using to generate some output. And these are typically implemented with traditional algorithms like greedy decoding, temperature sampling, or beam search. And if you're not familiar with those, I'll actually go over them in the first part of the talk. A meta-generator is a higher level algorithm. So we, again, take in some input and produce an output sequence. But now the meta-generator itself takes in these generation algorithms. And it can also take in other models or other functions, like the evaluation model or the calculator that I mentioned. And then a really key argument or parameter to the system is the budget for how much you're going to call the generators as you're going to generate an output sequence. So a really simple example is, let's say you call your language model API multiple times, and then you select the best output sequence according to some other model that you have. And again, you can use this to improve task performance by hopefully increasing this budget parameter. You can use it to combine multiple models like verifiers or retrievers with your language model. And as I mentioned, you can use it to incorporate external information like tools or feedback that you get on outputs. So this talk will first start off with reviewing how we just generate one sequence at a kind of low level from a language model. Then we'll treat that as a black box for these higher level meta strategies. And I'll go over four of them. So chaining, parallel generation, tree search, and refinement or self-correction. And then I'll talk a little bit about how we think about scaling these meta generation algorithms and how we get them to run fast in practice, which allows us to generate many, many sequences at a time. And so as Zaid mentioned, this is a kind of miniature version of a 2.5-hour tutorial we'll be giving at NeurIPS. There'll be an extended version of the first and the third sections by Matt and Haley. There will also be several code examples, a Q&A session, and a panel. And you can also check out our survey paper, which the content of this talk as well as the tutorial is all based on, if you want to read a bit more in depth about the things that I'm talking about. So first, let's talk about just generating one sequence with a language model. So these language models are autoregressive models, and that means that they decompose the probability of a full sequence into the product of these conditional distributions. And so each conditional distribution gives you a distribution over some prefix. You give it a prefix, like here is a prefix about Taylor Swift, and then it gives you this distribution over next tokens, which you can see on the right. Then what you can do is you can choose one of those tokens and put it back into the context, and then get a new distribution over your next token. And then you can continue doing this and eventually get a full sequence. And so to generate a full sequence, we use what's called a token level decoding algorithm. And these are really just concerned with how do you choose the next token. So you can view this as being some kind of search process through this exponentially large space of possible tokens. But if you call it a search, then there's a question, which is like, what are you actually searching for? What is the objective of the search? And then once you've defined the objective, how do you actually perform it? So at a really high level, if we're going to design some generation system, then you can kind of view the overall goal as designing some system that generates some notion of an acceptable sequence. So acceptability might be something that's really clear, like you're generating the solution to a math problem and you just want it to be correct. Or it could be something that's maybe harder to measure, which is like if you deploy your chatbot, are the outputs that it's producing acceptable or preferred to the users that are using the chatbot? And when you think about it, if all we have is a language model by itself, we can really only do two different things. We can either try to optimize over the output space, so try to find the output sequence that has the highest probability, or we can kind of treat it as a probability distribution and try to sample some output sequence from the model. So if we do this optimization, then this is referred to as MAP or maximum a posteriori decoding. And again, you try to find the most likely sequence according to the model. And so a really simple algorithm for doing this is called greedy decoding, which just goes step by step and chooses the most probable token at each step. So here's an example where we give the model this prefix, again, about Taylor Swift, and then at each step, just choose the most probable next token from the model. And this turns out to actually be suboptimal. So it turns out that if we would have selected the token singer, then we can end up with a sequence that's actually more probable. So this just kind of, gives you this lesson that these local decisions that you're making, such as in this greedy decoding, aren't necessarily going to be globally optimal. And so as a result, another method that's used is called beam search, where you could view this as a kind of tree search. And now you generate multiple possible next tokens. And here, for example, our beam is of size 2. So you would save the top 2 highest scoring tokens. Then you can expand those and again save the 2 highest scoring ones. And then you can continue this process until you eventually get a full sequence. Now, if you think about this, the greedy decoding is actually a special case of just having a beam of only size 1. So this is kind of a generalization of the greedy decoding method. And so beam search has been very, very popular. It was traditionally widely used in tasks like translation or earlier question answering systems. But in the era of the large language models, people started using the models and started to notice these kind of odd problems that were occurring with these optimization-based methods. And so it's kind of interesting. I don't know if you've used maybe one of the models from a couple years ago, but basically anytime you would generate with them, there was a chance that they would go into these kind of infinite repetitive loops. Like here, the model just starts repeating singer and songwriter. And so this is really puzzling, right? Because like sequences like this don't really occur anywhere in the training data, but they were still being produced. On the other extreme, if you really try to search for the most probable sequence, some researchers found that the model will actually assign the highest probability to these very short sequences. It'll kind of learn to put a lot of probability mass onto the kind of end of sequence token. And one way you could think about these is using this notion from information theory called typical sets. So at a kind of high level, what this is like if you were to flip 100 biased coins, then the most likely outcome from flipping those 100 coins is to actually have the sequence of all heads, right? Because if you just multiply these 0.6 together, then it'll always be higher than if you have any sequence with, even a single tails in it. However, if you kind of sample from this process of flipping 100 coins, you would almost never get this all heads sequence. It's like extremely improbable on its own, even though it's the highest probability sequence. And so this is potentially one way of thinking about these really repetitive sequences that for some reason the model is assigning really high probability from them. But if we were to just sample from the model, then we would get something that looks a lot more normal. And so this is partially the one reason that in practice, people more and more nowadays will use different variants of sampling from the language model.
Sean, may I
For
interrupt
example,
you? So, Sean, just one question is like, can you say a few words about like computational complexity of these various decoding options?
Yeah, sure. So that's another factor that's taken into consideration. So if you do this greedy decoding, then let's say you have T tokens, then you're just doing T steps of, like T forward passes with your model. Whereas if you do a beam search, now you're potentially well, you have to first of all expand each token, and typically what's done is to look at each possible next token probability, which could be expensive, and then your beam is going to be larger than size 1, so that can also increase the amount of computation.
Right. Thanks.
So then, yeah, so then if you look at like a typical language modeling API, it actually might not support beam search, but it'll have these different knobs for the sampling methods, which I'm about to tell you about. It actually does still have this repetition penalty, so I guess that issue still hasn't been completely solved. So to sample from these models, again, since they're autoregressive, you can do this kind of token by token sampling procedure. So first you can sample one token, then feed it back into the model and sample a second token, and so on until you get a full sequence. And so this will also be, you're just doing T different feed forward passes with your model. And again, since it's autoregressive, this is actually equivalent to sampling from the sequence distribution. If you want to go into a bit more detail, what this is doing is, you do this feed forward pass, and it gives you this vector, which are called logits, over your vocabulary. And then you take the softmax to get a probability distribution. And then this is itself a categorical distribution, which is really easy to sample from. And so this is a kind of nice property of these autoregressive models, that you can actually implement the sampling procedure in practice. Now, what's done in practice is to still adjust the next token distribution. So like you saw on that language modeling API, there was this temperature parameter. And so temperature refers to just dividing these logits before you take the softmax. And here's the kind of effect it can have. So as you lower the temperature, the distribution will get more peaked. And actually, if you were to take the temperature to 0, then you would get the greedy decoding. So just always choosing the peak of the distribution. On the other hand, as you increase the temperature, the distribution will become more uniform. The other thing that's done is to truncate the tail of the distribution. One reason for this is, maybe the model's probability estimates on the tail are kind of noisy. And so one heuristic is to just basically zero them out. So for example, you again saw on that LLM API, this top K. And what it does is it looks at the top K high scoring tokens, and then it'll just zero everything else out. Similarly, there's a method called top P. This will look at the cumulative probability of tokens up to, in this case, 0.9. And then everything below it, it'll zero out. And so, for example, you could see that like using top K in this case would actually prevent this short sequence behavior. You see, it's like zeroing out end of text, whereas top P wouldn't. So these things can have, different effects on the model. So that's a kind of whirlwind recap of how you just generate one sequence with a language model. And hopefully I gave you some idea of the things that are implemented if you're doing like an API call to a language model. So now next, we're going to treat these as black boxes and think about higher level patterns that you could have for calling these sequence generators. So again, our goal as a system designer is to generate a sequence that, build a system that generates acceptable sequences. This could mean correctness or human preferences. And we know how to sample things that are probable according to the language model. But there's an interesting question of like, what if these outputs aren't correct or aren't preferred by the human users? So there's really two key ideas that the meta generation algorithms that I'm about to tell you about take advantage of. One is that we can take advantage of information that is outside of the language model. So for example, let's say that we learned an evaluation model and then somehow used it during generation. Well, this could potentially give us the ability to select between things that are easy to evaluate, but maybe hard to generate in the first place. And these evaluator models can go by various names in the literature, ranging from critic to learned verifier, value function, reward model, and scoring model. I think in this talk, I'll try to use reward model, but it is pretty hard to consistently use just one word. So you kind of have to get familiar with just going between them. Then the second key idea is that we can call the generator more than once. So let's say we have some good evaluator model. Well, then maybe if we call the generator enough times, then we'll eventually find a sequence that is acceptable. So let's look at a concrete example. And now you don't have to read through all the math that is on the slide, but I'm just giving you a sense for the complexity of some of these things that the models can do. And in fact, today's models are actually much better than what I'm showing here. This is already pretty outdated. It's taken from roughly 1 year ago. So we have an input X, which is this math problem that we want to solve. And we're going to have the model output some solution Z, and then a final answer, which we'll call Y. And we can come up with the following generation strategy. We can just repeat this following procedure forever. We could have the model generate a solution, generate an answer, and then stop if our verifier says that the answer is correct. And we're going to assume just, for the purposes of demonstration, that we have an oracle verifier that can tell us, whether this answer is correct or not. Then if you actually do this with a wide range of language models, it can actually have just a dramatic impact on the ability to solve the problems. You can see here as on the x-axis, as you run and do more and more generations, on the y-axis, the accuracy with some models even goes up to 100%, or the percentage of problems solved. Now, you're probably saying, this isn't that realistic, right? Because like in every real world application, you're not going to necessarily have this oracle evaluator. In fact, you don't even have it for these math problems. And moreover, that strategy that I showed on the previous slide, it was kind of naive. It's maybe like the first thing that you would think of. And in fact, you could think of different strategies that involve calling these language models and incorporating things like verifiers. So again, that is the idea of meta generation, where we have some higher level strategy, G, which will itself involve calling these generation models. And then it'll also have other parameters like other models, the amount of tokens that we want to generate, and the overall strategy that we're using. And you can see that like these token level generators that I told you about in part 1 are a kind of special case where the system is only taking in the language model and your strategy is things like sampling adapters or doing beam search. So the first strategy that I'll tell you about is called chaining. And this is a really intuitive idea. So we basically we generate with a model and get some intermediate output, and then generate with the next model in our chain, and eventually get some final output. So a motivating example is the method that I mentioned before, And you could think of this chain of thought method as being a kind of two-part system. First, you generate this thought sequence, which is shown in green. Then you call your generator to generate a final answer. So this is a kind of simple, two-part system. But I think the interesting thing is you could think about generalizing this to more steps. And in fact, like several papers and several ideas take this approach. So here's a system called self-ask, and it basically generalizes this chain to be more steps. So in the first step, the model generates some query and then actually calls out to this external search engine and gets a response. Then the model can generate another query, call the search engine again, and you can basically just keep going until the model has enough information to finally answer a question. You could kind of view this as being a program in some sense, where your meta generator is the kind of outer program, and then your calls to the generator or the retriever, the search engine, are these kind of these functions within this outer one. And so this idea has come up in various forms throughout the literature. It's called things like language model cascades or LLM programs. And as you can imagine, there's many different ways of kind of piecing together and building these chains for different applications that you care about. It could range from things like rewriting the input prior to doing your final generation. Or you can actually get creative with it and decompose the process of generating a formal proof into three different steps, like sketching, filling in the gaps, and checking the proof. So the key idea is this chaining gives you a natural way of decomposing generation and also incorporating these other tools or models. However, when you think about it, just running one of these chains once is not really exploring the space of possible outputs. And so this will motivate the following strategies that I'll talk about, starting with parallel generation. So parallel generation, like it sounds, is a pretty simple idea. So we're going to call our generator multiple times to generate, say, n output candidates. Then we're going to pass those to some aggregation function, which ultimately gives us our final output. So one aggregation function that you can use is to take the maximum if you have some scoring function. So this is called best of n or rejection sampling. And so again, like concretely what you're doing is, let's say you're solving a math problem, you would generate n possible output candidates. You would pass them to this reward model or scoring model or evaluator model. It'll give you these scores, and then you simply return the output that had the highest score.
And
Okay,
just a question. So just a question, like when you call the generator multiple times, could you say a few words about like how you do that? Like how do you make sure there's, what are the assumptions on like all those generations like usually?
Yeah, so that's a good question. So what we'll do is you have a fixed input prompt, and then you're basically just drawing these samples, IAD from the model. So you can literally do it in parallel in the sense that like you can batch together the input prompts and then just, yeah, generate all n outputs at once. So they're all kind of independent of each other. Does that make sense?
Yes, sounds good.
And so why would you want to do this? Well, it's kind of easy to show that this is a good idea because it's in some sense approximating finding the most acceptable sequence. So in this first step of the approximation, you're saying that, sampling these n outputs is approximating the maximization over all possible outputs. And this is really cool because as you increase the number of generations or scale up the test time compute, then this approximation will get better. However, the second one can actually raise some issues. So it's basically saying that this reward model that you have, V, is ultimately approximating your notion of acceptability. So for example, let's say that your scoring model checks whether the math solution is correct or not. Well, it might not be perfect. And so you might actually find a solution that gets a high score, but actually isn't correct. And so it's pretty interesting. You can see this happen in practice, and it can be kind of drastic. So here's one of the really early papers from OpenAI that actually did exactly what I'm talking about. So they learned an evaluation model for scoring these math word problem solutions. And you can see that on the x-axis, as they sample more and more in their best of n procedure, eventually the system starts finding these outputs that are getting a high score, but aren't actually correct. So you see this drop in the actual solve rate. So we'll get back to how you could possibly improve the scoring model to potentially, alleviate the over-optimization. But another thing you could do is just change the aggregation procedure. So here's another really popular method, and it's called majority voting, or also called self-consistency. And so the idea, again, is pretty intuitive. What we're going to do is we're going to generate n outputs again, and let's assume that they all end in some kind of answer. So, you have your solution, your steps, and then you have some final answer. Now, you're going to choose the answer that just occurs the most often, so has the kind of majority vote. In this sense, we would choose, the answer 2. Now, you can incorporate the reward model, if you have one, and turn this into a weighted voting procedure. So now you can take your answers, pass them to your reward model, and instead of every vote just counting as 1, now you could weight each vote by the reward model score. So you can see here that, by doing this, we're able to break this tie between the answer 2 and the answer 4. So why would you want to do this? Well, first we could just look at the results, but then I'll kind of go through some more theoretical argument for why you want to do voting or weighted voting. So first, in practice, it's observed to just work pretty well. So here's an example on these math problems again. And you can see that as you scale up the number of generations on the x-axis, this weighted voting procedure is actually, opening up this gap with best of n or the majority voting. And so what is, how can we think about, what's going on here? Well, we can think about what would happen if you were to scale up the number of generations to infinity. So like if you had infinite test time compute. And it turns out that you can show that the accuracy that you get with the weighted majority voting converges to the following accuracy. It says that it's the accuracy that you get if you were to marginalize out or sum over all the possible intermediate paths prior to your final answer. So it's this nice kind of intuition that in some sense, what this is doing is it's aggregating information from all of the different possible paths that the model knows about to arrive at a particular answer. And then from this, you can get kind of 3 useful takeaways. The first is, if we were to keep increasing the number of generations, would it keep improving forever? And unfortunately, the answer is no. because what this is saying is you will converge to this accuracy shown here. Second, when is actually using this weighted voting procedure better than using voting? Well, we could basically look at this quantity on the inside, and it basically says that, okay, if your weight times your generator tends to assign more probability mass to correct answers than just the generator alone, then you can expect to do better with the weighted voting. So intuitively, if your, voting function is kind of slightly better than your model at scoring the outputs, then this is a pretty good procedure to use. Second, like given that we're going to converge to this accuracy, how could you potentially improve performance further? Well, you could either improve this reward model V, or you could improve the generator G. That could be with a bigger model or a better algorithm. So improving the reward model is itself an extremely active area of research. And just for fun, you could actually think about using the techniques that I just mentioned in the evaluator or in the reward model itself. So here's a paper and it's called generative reward model. And they basically say that like, okay, in order to evaluate an output, we're going to do this majority voting procedure. So we're going to generate multiple chains of thought, come up with some evaluation score, and then take the average. So creative ideas like this are, being looked into right now. And as you improve the performance of the reward model, it'll improve the performance of the search algorithm. So in summary, these parallel meta-generators explore the output space, and in practice, they're actually very effective. However, they're ultimately bounded by the quality of the evaluator and the generator. And so one insight is that these are really only using the verifier at the very end. So basically, we generate a full solution, and then we finally use the verifier to, select or aggregate the outputs. So the next two methods I'll talk about will try to do a bit better by somehow leveraging evaluation on intermediate parts of the generation procedure. And so in particular, next I'll talk about tree search algorithms. So a tree search algorithm will assume that your generation breaks down into the sequence of kind of states and actions or nodes and edges. So at the first, so you might call your generator and get, for example, the first step of a mathematical solution. And you'll come up with some score for these possible next steps. If you're able to do that, then you can use some kind of tree search algorithm to do, a depth first search or a breadth first search or whatever strategy you want to use. And you can eventually get some output sequence. So the design choices are, what are your states? Like in the case of a math problem, your states might be a step of a solution. And then how do you get these scores for each node in the tree or each state? And then finally, what search strategy do you actually use in practice with a language model? So let's look at a concrete example of doing this again for the math problems. And in order to get the scores, the method that's used, it's called a process-based reward model. So a process-based reward model will take in the solution steps that you have so far, and then it'll be trained to predict, is the solution so far correct? Or alternatively, like, will this solution eventually be correct? So the kind of like expected future return. And if you're familiar with reinforcement learning, this would correspond to a value function. And so you can either train this with human annotation. So a popular paper from OpenAI they actually hired human annotators to annotate each one of the steps. Or you can take a model and generate a bunch of continuations and get some approximation of the expected reward. So now let's say you have one of these scoring models, then you could set up a tree search that kind of goes step by step. So here's an example tree search strategy, one that we recently developed, and it is specifically designed for these process-based reward models. So the idea is pretty intuitive. Let's say that we're generating step by step, and now here are the next step candidates that our model gives us. Then we're basically going to use the reward model to determine which branches we should explore next and how much we should explore them. So like in this case, this first branch, I mean, it says that 2 + 2 = 5, so we don't really want to explore that one further. This one says that 2 + 2 = 4, so maybe that's a promising path. This one we're not really sure about, or at least our reward model is not sure about it. So we'll allocate some exploration budget to it, but maybe a bit less. And then concretely, what we do is pretty simple. We just look at all the nodes that we have in our current frontier, and then you just take the softmax over their scores, and that'll give you a budget for each node. Now you can kind of view this tree search procedure as an alternative to doing parallel sampling. So you're going to basically run the tree search, get some output solutions, and then you can pass them to an aggregator like majority voting. And so in doing so, you can kind of compare them on an equal basis with just doing parallel sampling from your model. The key idea is that the tree search is able to potentially take advantage of these intermediate scores. Like for example, with the 2 + 2 = 4 example, we didn't waste our compute budget on exploring that one further. Instead, we allocated it to a more promising path. Here's an example showing comparing this rebase tree search against sampling combined with the weighted majority voting. And here the comparison is being done on a kind of equal compute basis. So we're equalizing the amount of tokens that are being generated with each algorithm. And you can see here that it is possible to use the tree search procedure to get a lower error, almost by 5%, compared to doing the parallel sampling procedure. Now, can you use tree search for everything? I think, I mean, it's an open question, but we could certainly look at what conditions are required to use a tree search meta generator. Well, one is that your task has to have some kind of decomposition into steps. This is pretty natural for things like math problem solving or generating a formal proof. You also need some good reward signal because that will help you train this value function or the scoring function for your nodes. And then also you have to be able to reset the environment. So like if you are doing backtracking within the tree search, then you might have to kind of like roll back to a previous step of the environment. And this isn't always the case, especially with some of the modern agent environments that language models are being used in recently. Nevertheless, there have been success cases with tree search. One that didn't involve language models but was extremely successful was the use of tree search in AlphaGo. And then in the area of formal theorem proving with language models, which I won't have time to go into now, but I'm happy to take questions about it. Tree search is basically the standard that you use to build any type of state-of-the-art system. So finally, I'll talk about a strategy called refinement.
And perhaps we can do a short pause here to take some questions.
Yeah, sure. Yeah, I've been talking a while.
Any question from the audience?
Hi, I have a question. So in the tree search, do you change the input to the model as you keep going forward, or do you just, yeah, every time I use the API as I go down the tree, am I just increasing the context with the previous output, or am I doing something smarter?
Yeah, that's a great question. So in the example that I showed before with the math problems, there you are just appending the steps to the previous context. But in other cases, you might actually have some interaction with an external environment. So like in these formal theorem provers, each time you generate a next step of the proof, the proof assistant or the environment will actually give you a new state. And so in that sense, you're adding extra, new information into the context.
Yeah, sure.
Okay, cool. So yeah, next
I'm
I'll
sorry.
go. Oh, sorry.
My bad. In one of the earlier slides, you showed that the chain of thought prompting performance increases together with model size. Is it can we decide that larger model are better at chain of thought, and can we get some chain of thought gain from smaller models as well?
Yeah, that's a great question. So I would say that early on in the literature with chain of thought, it was viewed as a kind of emergent capability. And so it was kind of mysterious. And it seemed like, yeah, you basically needed a larger model to do the chain of thought. I think since then, we found that, especially if you do the post-training and include a lot of chain of thought data, then even with fairly small models, like if you look at the most recent llama models that are released, I think even the smallest ones that they release will to some extent be capable of doing the chain of thought. Now, if you still look at the absolute performance on a given benchmark, yeah, you'll still tend to have the highest performance with the largest model. But I would say that, the smaller ones are still capable of doing something.
Questions? I mean, I guess we can go on to the section on refinement.
Okay, great. So yeah, the last strategy is called refinement or self-correction. And here the high level idea is also very simple. It's that we want to start out with some generation that is imperfect or bad, and we want to produce a generation that is better. Okay, so very simple idea. Now, when you look at how this is done, it turns out that there's a few moving parts in practice. In particular, one thing that you might do is you might, initially generate your imperfect output, and then you might try to get feedback from a model. So here this model says, 2 plus 2 equals 5 is wrong. And now you can imagine that if you pass this generation along with this feedback to the correction model, then yeah, hopefully it should be able to produce a better generation. And so what happens in practice is the quality of this feedback model, or the source of feedback, turns out to be really important for whether this refinement ends up working or not. And so actually you can get a really good insight into this idea of the dependence on feedback through a kind of toy problem. So it might be small. Next time I'll make the picture bigger. But the task here is going to be generate Taylor Swift, and you want to just generate it one character at a time. And we're basically going to use the simplest possible language model. So the model can only produce one character at a time, and it doesn't take in the other characters. So if you do this, you usually get something pretty random because you have to essentially sample all of these 11 characters in parallel and hope they end up being Taylor Swift. Now you could pass this to a feedback model, and our feedback system is going to tell you exactly which characters are correct and which ones are incorrect. So that's highlighted here for the first step in green. Now you can have this corrector, which only regenerates the incorrect characters. Okay, so you can see that like after doing this, you get a few more characters that are correct.
Could you clarify, like the feedback, is it provided sequentially or after the sequence has been generated? Then you get the feedback.
Yeah, so it's kind of the picture on the previous slide where you generate, the full sequence, and then you get feedback. But then you can try again. So you can generate a correction, get more feedback, and basically go in a loop. And so the idea is that like, this could potentially take advantage of this really fine-grained feedback, which tells you exactly which characters you should be changing. And if you run this simulation, then you can look at the red line, and basically doing best of n is hopeless because you're always just sampling these 11 characters. You can check whether they're correct or not, but then you don't have the opportunity to kind of keep improving the sequences after they're generated. In contrast, the refinement procedure is able to like gradually make these corrections and ultimately get an optimal sequence. Now, I know what you're thinking again. This might not be that realistic because in some sense, we have this oracle, which is telling us exactly which characters we need to correct. And in fact, if you add a little bit of noise to that feedback, then you can basically control the performance of the refinement system. So in orange, with a little bit of noise, you no longer get optimal sequences. And with a lot of noise, you actually end up doing worse than best of n. And so this is a kind of gives you some good intuition of what I'm about to tell you about with the concrete kind of real world refinement systems. Sometimes you have very good feedback and the refinement does very well. Other cases, you're not able to get very
Sean?
reliable feedback.
Sorry, can I ask a question?
Yeah.
Just on these refinement systems, is it true that if the feedback and corrector are of arbitrarily high quality, can you just replace the language model entirely with random noise or randomly generated tokens? Have you ever tried this just as a full replacement for language models?
Well, I guess you would need some like feedback source, which is basically telling you exactly which output to generate, which might be difficult, right?
So what is an example of like a maybe real world feedback system?
Yeah. So that's a great question, which is where I'm going next.
Thanks.
So you can kind of separate the refinement systems.
Yeah. Sorry, just one more question before we go further.
Yeah.
So maybe in the so like a chain of thought and so on as this proof of concept that by doing a lot more inference you can increase accuracy, right? But if I draw the connection to like in context learning versus things like prefix tuning or soft prompting, right? Then it's known that like soft prompting is more effective and more efficient than in context learning. And actually, you can train soft prompting with in context in context learning as a teacher. So is there a similar thing done here, which is that you first do this chain of thought stuff and then you like update the model itself so that it can incorporate its gains without having to go through so much inference?
Yeah. So that's a really good question. So I would say, I guess, a few things. So one with the chain of thought in particular, it can have the ability to say like decompose a problem into multiple steps. And there's been some work which shows that this could potentially increase the computational capacity of the generation system. So if that was the case, then maybe you have to do, more steps of computation with the transformer. But if that, always isn't the case, then you certainly can train the model to basically, learn what is the probable output from, say, like best of n. So yeah, you can, in some sense, like amortize some of the inference time compute by further training the model.
Great, thanks.
So yeah, so one extreme is you have this kind of external information source that is providing feedback. And a really kind of natural setting for this, one place where refinement has been pretty successful is in code generation. So let's say you generate some buggy code on the left. And then here's just one example. This is maybe an extreme example, but for some Rust code, you can actually have this formal verifier. And the formal verifier will, first of all, tell you whether your code passes or not, passes the specification. It'll also give you these very detailed error messages. So like here, it's actually like highlighting this one line of code, like line 23. And so if you pass that to your corrector model, then, there's probably some hope of the model being able to take advantage of it. In this example, the model actually does make a fix, and it happens to be right nearby where the feedback was from. So this is an example where, you have this verifier, or you might have a compiler or a code interpreter. And in some sense, it's providing you some new information that the original language model doesn't have access to. And in fact, that's like where the current successes of the refinement have been. Things like code interpreters, or if you have, a human expert provide feedback, or if your feedback model, calls out to some external retriever model, then in some sense, the feedback step is adding something new to the generation system. Then another case is like you could try to take a language model and then basically reprompt it so that it gives itself feedback. So for example, let's say you're solving the math problem, then you could prompt it to say, look at this, is it correct or not? If it's not correct, give me some feedback, and then you can pass that to your corrector. Here, this is, a lot more mixed. So it's like those kind of noisy lines that we saw in the toy example. In some cases, the models actually can reliably evaluate some tasks. So a good example is like, let's say you ask the model to generate some document that has 10 different citations. And the model generates a pretty good document, but it only has 9 of them. Well, then the model can actually notice that one of them is missing, provide that as feedback, and then you have this very kind of local change that you can make, and the refinement system works. On the other hand, one thing that's been found is that, if a system has a certain level of reasoning ability, then it's not as clear whether the model can kind of provide its own feedback about its reasoning. So here's a result from a kind of famous analysis paper that I linked to down here. And it basically shows that the model will just as often move from being correct to incorrect than it does, going in the other direction. And so this kind of shows that the model is struggling to give really high quality feedback on its own outputs. Then the final case is kind of intriguing, which is like, what if we actually don't do any feedback at all, but we try to train a model that directly learns how to improve outputs? And so this might sound kind of crazy at first, but imagine that you train this with some kind of reinforcement learning, where the model kind of sees all of these different examples of going from some suboptimal output to one that is slightly better. Well, then, I mean, these sequence-to-sequence models are, pretty general purpose. It is plausible that, maybe the model could learn how to go from something that is imperfect to something which is better. And so there's been a few different algorithms that have tried to do this, and they generally take the form of generating some trajectories. So those will include things that are, correct, some that are incorrect. And then you use some reward function to basically like order them. Then you can actually train your model to produce the good outputs and then repeat the procedure. There's been a really recent paper, a really interesting paper that showed that you kind of have to be careful when you're training in this way. In particular, the model can actually learn these kind of degenerate strategies. For example, it could learn to just ignore this initial input. And so in some sense, it's not really a corrector or refinement model. However, this paper called SCORE came up with a regularization procedure and a reinforcement learning procedure where they were able to achieve some amount of the self-correction. So here's an example that they had where this sequential corrector was run for multiple iterations, and it actually does better than the parallel sampling. However, if we kind of take a step back, whether you can enable this self-correction behavior and how to do it, especially in a really general purpose way, is very much an ongoing area of research. So in summary, the refinement methods, if you have a really kind of reliable extrinsic sort of feedback, then there have been some positive results. If you're just kind of reprompting a model, then it can work, but the results have been mixed. And then if you're going to train a model to directly learn to self-correct, that again is itself kind of an ongoing research area. So that's it for the strategies. Now I'll talk a bit about scaling up these meta generators. So one question to ask is, I told you about all these different meta generators, but how do you actually choose between them? So what we want to do is choose between them, not just based on task performance, but also based on compute cost. And so in particular, the cost of a meta generator is going to be based on the model size that you have, as well as the number of tokens that you're generating. And you could formulate this as a problem which is called compute optimal inference. So it says for a given compute budget, you want to choose the number of model parameters or generated tokens and inference strategy that minimizes your error. So basically does best on the task that you care about. So once you formulate this problem, you can ask different questions. Like one question is it better to use a small model and kind of generate more, or use a large model and generate a smaller number of times? If you fix the strategy and kind of run this for many different model sizes and many different number of tokens, then you can get this what is called like a compute optimal frontier. So what this is showing is like for different model sizes at different inference compute budgets, what is the performance that we get? And so what you want to look at is like, okay, for a given inference budget, let's say 128, what is the model size that achieves the best performance? And it's pretty interesting that like at some inference budgets, it's actually better to use a smaller model and generate more often. You'll get lower test error and better performance. On the other hand, if you really want the best performance, at least in our study here, it's still beneficial to just get a large model and just keep running it for longer and longer. That's like the very right-hand side of this curve. You can also ask, out of these different meta generation strategies that I've showed you, what is the compute optimal one if we kind of evaluate them all on an equal computation basis? Here's showing another one of these frontiers where now we're additionally varying the search strategy. Again, here for mathematical problem solving. We can see here that this tree search procedure, rebase, turned out to be compute optimal over all of the different inference budgets. So for example, if you do the parallel sampling, like in blue here, it performs a bit worse. And then if you use this more sophisticated Monte Carlo tree search algorithm, which I didn't have time to go into the details of, it turns out to be a very expensive algorithm. So once you evaluate it on a kind of equal basis in terms of the compute cost, it actually does quite poorly. So in summary, this idea of compute optimal inference is to choose a meta generator that not only has the best performance, but to also look at the test time compute budget. And in doing so, you can, in some sense, like allocate your test time compute. So now in the last part of the talk, I'm also happy to stop early for questions because Haley will actually do a full section on speeding up meta generators at the NeurIPS tutorial. But if you'd like, I can give you just a quick overview of different ways of speeding these up in practice.
Maybe Sean, I think there's another talk coming up, so maybe we can just wrap up.
Yeah, that sounds good. So let me just jump past the speeding up section. Again, Haley, who is an expert in the area, will give a full expanded version of it. And yeah, just conclude that, again, we saw these meta generation algorithms, which give you different strategies. They let you spend test time compute to improve performance. And we can combine them and interpolate them, and then use these trade-offs to choose and design them. So I think moving forward, we're going to see, things that combine these different ideas. So like combine tree search with refinement, for example. And then I think there's like a lot of interesting outgoing research paths. One is how can we achieve this this behavior that we see with this O1 model of like the model being able to learn to search on its own. How do we incorporate these meta generation algorithms into reinforcement learning? And how do we have, even more fine-grained compute optimal generation that maybe like dynamically is allocated based on the input? And then, of course, many of the conclusions that we've talked about are ultimately just due to a few tasks. And so also just using these in a wider variety of settings is incredibly important for both practice and for science. So again, we'll have a full tutorial at NeurIPS. We have a survey paper on this topic, and all of the content in the slides and in the survey paper is all due to this amazing team shown here. And so I'd like to thank all of them. And yeah, happy to take questions now. Also, feel free to send me emails after, because yeah, I love discussing this stuff. So, and thanks again for the opportunity to give the talk.
Questions? Yeah. So one question is this talk was focused on meta generation for like sequential data, right? And so is there can one envision like similar frameworks or similar or like different approaches for like data that is not sequential, that is structured in a different way, like images, videos, and other things.
Mm-hmm. Yeah, that's a great question. I mean, one thing is that if you look at a, diffusion model, then you do have some natural notion of, potentially running the model for longer and potentially getting some better performance. So yeah, with the different generative models, you do have this potential knob, with the test time compute. Now, I don't necessarily know how, that would compare with the exact knobs that we have in language. But I think like if you were to combine the two things, then you could have potentially something pretty interesting, because now we're developing the techniques for the sequential models. And yeah, the meta generation kind of gives you a framework for potentially incorporating them with these other types of generative models.
And another question is like we draw all these scaling laws, right? Like the training one, the post-training one, the testing one, right? And it does show that, theoretically optimal algorithms may not be that optimal when we look at the actual distribution of the data. And then other algorithms which may not seem optimal or like, desirable turn out to be more like effective. But what does it say on like the data distribution? Like what have we learned from these scaling laws in terms of the distribution of natural text?
Yeah, that's really fascinating question. So I think one thing, so if you look at like the difference between pre-training and post-training, there's this idea of there being some misalignment. So if you actually model all of the text on the internet, then you might model some text which is like offensive or has buggy code or things like that. And moreover, like the text isn't necessarily formatted for the task that you care about. And so potentially you can get some gain by doing this really general purpose pre-training, but then still shifting the model's distribution towards the task that you care about. I think there's also a notion of like if you just look at the language model, what are the capabilities which are like not contained in the language model? And one really natural thing there is if you look at like really up-to-date information, then no matter how much pre-training you do, that information is not going to be in your model's parameters. And so you have to come up with some strategy for getting around this, whether it is training your model so it can use a retrieval system. It might be, having a really long context, some combination of the two. So yeah, I think it tells us that, yeah, maybe modeling this distribution is giving us a really good starting point, but you still need to kind of shift it a bit. And then second, there are some cases where your model is not going to be able to basically store everything that is needed for the task.
What opportunities do you see in maybe training these models to be a part of a larger meta generation system? So as opposed to just modeling text, also modeling interaction with other parts of a meta generation system?
Yeah, so I think there's a lot of different parts. There's a lot of different ways to take that. So one is like you could look at the refinement algorithms, for example. And what I was basically saying is that like if you just reprompt the model without specifically training it to do the correction, then you're probably missing out. Because like, for example, in the model's pre-training, there's maybe not that many examples of like incorrect mathematical solutions, or like, you know, repairing them into a correct one. And so potentially with like specific training strategies for those existing components, you can improve the meta generator. There's also a variety of other things you could think of, like let's say you want to reallocate the compute that you're using. Then how do you have some learn system which says, you know, given this input, which meta generator am I going to call, or like how much compute am I going to allocate to this problem? And then at like another level, you could actually imagine like learning the whole configuration of the meta generation system. You might frame this as like a new type of computational graph. And then you have this problem of like, okay, finding the computational graph that actually gives you the compute optimal meta generator. So these are like some things that people are starting to look into. So I guess they're not too crazy, but they're definitely exciting. Yeah, exciting next steps to take.
So on that note, let's thank the speaker.
Thank you.
Thank you, Sean.
Okay, thank you. Okay, thank you. I'll log off then.